Okay, so hello everyone. My name is Young Cha and I'm an assistant professor in the Department of Computer Science and Engineering. So it's a pleasure to meet you all. So this week we will begin with a gentle introduction to this course, Introduction to Software Engineering. So I think I've been teaching this course since 2022. So in this course we will explore both fundamental concepts and recent techniques in the field of software engineering. So let's begin with a brief overview of what this course is all about. Okay, so let me start by briefly introducing myself. I joined 성균관 University as an assistant professor in 2021. So here is my email address in case you would like to reach out. And currently, I'm leading the software analysis lab. We usually call it CEL. So this is the link to my homepage. So if you have time, feel free to visit it. So you will find information about my research area, publications, traverse portal, and more. So broadly speaking, my research lies in the field of software engineering. More specifically, my expertise is in the software testing and program analysis. And I'm also interested in applying machine learning techniques to address the various challenges in software engineering, such as bug detections and program repair. And I mainly publish the papers in the top tier conference in our field, including XE, FSE, and ASE. And currently, our lab consists of 6 graduate students and myself. And this photo here was taken in San Francisco during the FSE conference together with my student. And for your interest, this is me. By the way, I'm looking for a few motivated undergraduate students to join our lab. So if after taking this course you find yourself interested in research, feel free to send me an email. This email. Okay, that's all for my brief introductions. Now let me introduce the 4 main objects of this course. The first goal is to help you gently build solid foundations in software engineering. So to achieve this, we will be using the textbook Software Engineering, the 10th editions by Ian Somerville. So as far as I know, it's one of the most widely used and respected textbook in this field. So the book is divided into 4 main parts. In this course, we will mainly focus on part 1, Introduction to Software Engineering. So this section covers essential topics such as the software process, agile development, system modeling, testing, and more. So from part 1, we will learn about how the software is developed as well as various methodologies used in this process. So since this section is under 300 pages, I highly recommend reading it full. And if you find the English version challenging, a Korean translation is also available, so feel free to use it as needed. To sum up, the first course objective is to provide a broad and accessible introduction to the software engineering. So my tentative plan is to focus on part 1 of this textbook up until the midterm exams. So I know this part 1 may feel a bit dry or theoretical, but it is very fundamental knowledge, especially for computer science majors who plan to work in industry. And the second objective of this course is to give you hands-on experience with the labor-intensive aspect of the software engineering. So in practice, software engineering involves many tedious and repetitive, yet critically important tasks. So this simple diagram with 4 boxes illustrates the basic flow of the software development process. First, we begin by specifying the software, which you can think of as defining its expected input and output behavior. Next, we implement the software to meet the given specifications. However, as you probably experienced, the code often doesn't work exactly as intended. But that usually means there's a bug somewhere in the source code. And so to uncover these hidden issues or vulnerabilities, you need to thoroughly test this software. So once bugs are identified, we have to fix them carefully, making sure not to introduce new ones in this process. So by repeating this cycle of testing and fixing, we gradually move toward safe and reliable software. Even though the process looks straightforward, every step requires significant time and effort. So in this course, you will get a chance to experience this entire process for yourself. More specifically, the first potential task will involve the manual task case generations. For example, I will provide you with an open source C project such as Grep, a widely used text search utility. Your task will be analyze this program and manually design the high quality test cases, like the ones shown here, such as TC1 and TC2 highlighted in blue. So in software testing, the effective test cases are those that maximize code coverage or help trigger the hidden bugs in the programs. The second potential task will be manual bug fixings. So I will provide you with a simplified buggy program that contains common errors such as null point exceptions or double-free, UGF-free memory issues. So your job will be to examine the faulty program and manually create a corrected versions, a patch that eliminates this bug. So in other words, this task is designed to give you hands-on experience with the labor-intensive debugging and repair work that is central to software engineering. The third object of this course is to explore the latest techniques in software engineering. So in fact, many of the tasks we discussed it earlier, programming, testing, and debugging, are now being automated in the modern software engineering research. So automated programming is known as the program synthesis, and automated test case generation falls under the software testing, and automated debugging is referred to as automatic program repair (APR). So in this course, I plan to introduce and guide you through the cutting-edge techniques such as symbolic execution, gray box fudging, static analysis, and program repair, program verifications, and more. So I believe many of the most exciting and engaging lectures will be take place after the wisdom exams. The final objective of this course is to give you experience working on a team project. So when developing software on your own, you might not feel the need for the formal software engineering techniques. So in fact, when you are working solo, the fastest and the most efficient approach is often just diving straight in coding. However, once you graduate and join a company like Google or Samsung or Naver, things changes. You will need to collaborate and communicate with your team members effectively. So in industry, commercial software often contains millions of lines of code, far too much for a single person to handle testing, debugging, or development alone. So in the case of the safety critical software, even programs with just a few thousand lines require extensive verification work. So my goal is to help you gain indirect but practical experience through a small-scale team project. Okay, to summarize, This course is designed with four main objectives. First, to help you build a solid foundation in basic principles of software engineering. Second, to give you hands-on experience with the labor-intensive tasks involved in the real-world software development. Third, to introduce you to state-of-the-art techniques used in the modern software engineering. And finally, to provide you with practical experience through a team project. Okay, so now let me go into more detail about some of the topics we will cover in this course, software engineering. So first, as you can see here, we will focus on software testing, which takes any given program as an input and aims to find inputs that trigger bugs. In particular, we will cover two simple but important subtopics. So I will start by briefly explain why software testing is necessary to motivate the need for it. Then I will introduce white box testing with a focus on symbolic executions, more specifically concrete testing. Alright, so let's begin with the necessity of the software testing. First, as you all know, there's no doubt that software is everywhere in today's world. So let me ask quick questions. So how many software programs do you think exist globally today? 10 million, 100 million, 1 billion, or even more than the 10 billions? So take a moment and choose one of these options in your mind. Yeah, the answer is I don't know either. So I was really curious about how many software programs exist, but I could not find any official statistics on that. So the number is simply too large to count. Instead, I came across some interesting statistics about the number of software developers around the world. According to this article, the number of software developers worldwide was about 24 million in 2019. That number is projected to grow to 28 million by 2024 and reach 4 million by 2030. So, in other words, the first key point is this: software is everywhere. And unfortunately, just like software is everywhere, software bugs are also everywhere. So I brought in a few infamous examples of software failures. One of the worst software bugs in history was this: the explosion of the Ariane rocket. The European Space Agency spent nearly 10 years and $7 billion developing this Ariane rocket, but due to a very tiny software bug, this incredibly expensive rocket exploded just 37 seconds after launch. So this cause is a data conversion error from a 64-bit floating point value to a 16-bit integers, which lead to an integer overflow. So if you're curious, I've included a new YouTube link where you can watch the explosion of the Ariane rocket files. In addition to the Ariane rocket explosions, these articles highlight other serious accidents caused by software bugs. For instance, as shown in the second article, several patients lost their lives due to radiation therapy machines, all because of software race conditions. And another article explains the batch overflow exploit, where attackers were able to generate an enormous number of tokens, even trillions of the Ethereum tokens, and deposit them into regular wallet addresses. So this exploit made many ERC20 tokens highly vulnerable to price manipulations. As a result, several major exchanges had to temporarily suspend ERC20 token deposit and withdrawals. So cases like this show us that one of the fundamental challenges in software is bugs are everywhere and they can have serious consequences. Okay, so let's return to our first questions. Why do we need to software testings? The answer is simple. We don't want to lose our money, our time, or even our lives. So due to these software failures. So that's why software testing is essential to catch serious bugs early in the development process before they cause the real harm. So I think by now we are all convinced of the importance of the software testing. So next, let's ask, how can we describe software testing in general? At a high level, software testing can be viewed as a technique for automated test case generations. So this technique usually takes a target program, such as a binary file or source code, and tries to generate inputs that are likely to trigger bugs or cause the program to crash. So in general, a single test case is simply an input that executes the programs. So for example, if we have a function foo int x and int y, then a pair of concrete value for x and y would form a single test case. Of course, developing the program, depending on the program, the input might be more complex, such as command line string or PDF file or JSON document and so on. So still the main goal of the software testing is the same, to automatically generate inputs that expose bugs. So that's why software testing often also referred as automated test case generation techniques. However, in real-world programs, software testing techniques often struggle to pinpoint where the bugs are located because of the high complexity of the modern software. More specifically, the number of possible executions grows exponentially with the number of branches. And in practice, a typical real-world program might contain over maybe 10,000 branches, which means we are dealing with 2 to the 10,000th possible paths. Clearly, it is impossible to explore all of them in the reasonable time. So we simply don't know where the bug might be hiding among these enormous number of paths. So that's why I borrowed this line from this movie Taken. I don't know where the bug is, but I will find it and I will kill it. Anyway, but do you guys seen this movie Taken? If not, well, let's skip it. Anyway, rather than trying to find software bugs directly, software testing often focuses on increasing code coverages, which is something we can actually measure and track. Intuitively, code coverages tell us how much of the program's source code is executed by the generated test cases. For example, in these illustrations, the green lines represent the part of the code that have been executed, while the red lines are parts that have not been touched yet. So in testing, the goal is to maximize those green lines to execute as much of the program as possible within a limited time budget. So the next question is, how do we care so much about increasing code coverage in software testing? Is it really important? The underlying idea behind increasing code coverage in software testing is this. the more code we execute, the more program logic we exercise, and the more bugs we will likely to uncover. So let's consider an example. Imagine you have to choose between two self-driving cars. The software in the left car has only executed 10% of its total code. Meanwhile, the software in the right car has executed over 90%. So which one would you choose to ride in? Or you just decide to walk? I think most of us would definitely choose the car with 90% code coverages. Why? Because we naturally believe that the more of the code program logic has been tested, the safer and more reliable that software is. So now let's dive a bit deeper into what code coverage actually means. Okay, let's take a look at some common code coverage metrics: line coverage, branch coverage, and task coverages. First, line coverage is the simplest one. So it is calculated by counting how many lines of code have been executed so far. So in this code shown in here, this one, the test case consists of a pair of integer values x and y. So here's a quick quiz. So what's the minimum number of test cases needed to cover all 6 lines of this code? And what specific values should that test case include? I will give you about 10 seconds to think about it. Alright, so we can achieve 100% line coverage using just one test case. The answer is x is 90 and y is 25. Now the second metric, branch coverages, is a bit more fine-grained than the line coverages. Branch coverage is calculated by counting how many the conditions have been exercised. So as might recall, each if or while statement introduces two branches, one for true and one for false. So in this example, we have two conditional statements, which means a total of the 4 branches to cover. So here's the next questions. What's the minimum number of test cases needed to cover all 4 branches? And what values should be those test cases have? I will give you about 10 seconds again. Yes, the answer is we can achieve 100% of branch coverage with just 2 test cases. For example, the first test case, x equals 90 and y is 25. This covers both these true branches. And second test case, x equals 0 and y equals 0. This covers both these 4 branches. Of course, there are other combinations that would also achieve full branch coverages. For example, x equals 90 and y equals 0, x equals 90 and y equals 0, and x equals 0 and y equals 25. These all cover all branches, just in a different order. Lastly, let's talk about the path coverage, which is even more fine-grained than the branch coverage. The number of execution paths in a program typically grows exponentially with the number of if or while statements. So in this example, we have 2 if statements. So the total number of possible paths is 2 to the 2, which is 4. So now here's the final questions. What's the minimum number of test cases required to cover all paths? And what are the values of those test cases? Take 10 seconds and try to write down the test case yourself. Yes, the answer is to achieve 100% of pass coverage, we need at least 4 test cases, one for each of the unique execution passes through this code. More specifically, the first test case covers the execution path that goes through these both 4 branches, and the second test case covers another unique path, and the third test case yet another different path. And the fourth test case cover the paths where the both branches, both conditions are true. So as you may have noticed, a single test case can often cover multiple lines or multiple branches at once. However, when it comes to path coverages, each test case typically covers only one unique path through the programs. So in general, achieving full path coverage is much more difficult than achieving the full branch or line coverage. However, full path coverage is also more powerful when it comes to discovering path bugs. That's because path coverage explores the program's logic at a much finer level of the granularity, which means it exercises a wider variety of the execution behaviors, making more likely to expose hidden fault. Alright, now let's take a look at the software testing method used to achieve high code coverages. At a high level, we can categorize this method into black box and white box testings. The key difference between them lies in whether or not the source code is used during the test case generations. The black box testing takes only the binary as the input. It executes the program without observing or analyzing the source code. This makes it fast and inexpensive to generate test cases, but it relies heavily on randomness, so it's generally naive and unstable. On the other hand, white box testing uses the source code to systematically decide how to generate test cases. So it's a more structured and guided approach, but it tends to be more expensive per test case. So there's also a third category, gray box testing or gray box fudging, which combines elements of the both black box and white box methods. So it observes part of the source code, so it's more informed than the black box, but cheaper than for white box testing. So today we'll focus on a specific white box testing method called symbolic executions. Symbolic execution is a powerful software testing method that's widely used in both academia and industry. Simply put, the core idea is to replace concrete input with symbolic variable and then execute the program symbolically rather than with the fixed value. So I will explain how symbolic execution works using a simple code example shortly. So here you can see some well-known symbolic execution tools used in practice. For your interest, the last two, the Chameleon and Homie, are tools I developed myself. In particularly, I named the Homie a traditional Korean gardening tool because it helps prune away unnecessary execution paths in the programs, thereby focusing only on the passes that are used for the bug detections. In any case, symbolic execution is a very practical and effective testing technique. For example, the symbolic execution tool Sage, developed by Microsoft, was able to discover 1/3 of all the bugs found during the development of the Windows 7. And catching this bug early on ended up saving Microsoft millions of dollars. And another example is Java Pathfinders, a symbolic execution tool that successfully uncovered a serious bug in NASA's flight softwares. So this shows that symbolic execution tool isn't just a theoretical concept, it's a powerful and real-world technique for detecting critical software bugs. More specifically, modern symbolic execution is often referred as dynamic symbolic executions. There are two major variants of it, concurrent testing and execution-generated testing, EGT. So concurrent testing was first introduced by Kaushik Sen, a professor at UC Berkeley, and EGT was proposed by Christian Carter, a professor at Imperial College London. Both are considered dynamic symbolic execution techniques because they combine concrete execution with symbolic executions. However, the way they operate internally is slightly different. And don't worry, we will cover how each method works in detail. Uh, in today's lecture, I will walk you through how one of the main approaches to dynamic symbolic execution, which is the concrete testing, actually works. So as you can see this name, concrete is a blend of the words concrete and symbolic, just like how the words brunch combines breakfast and lunch. Okay, so first let me show you a limitation of the random testing using these simple 10-line programs. So as you can see, the program takes two integer inputs, x and y, and it then assigns a value to the z by calling these twice functions, and includes the two if statement involving x, y, and z. So here's a quick quiz for you. So if the values of an x and y are randomly choose between the 1 and 100, what is the probability that you will reach the error branch in these programs? You choose one of the four answer options, these four options. So I will give you 10 seconds to think it through. The answer is 0.4%, even though the code is quite simple and the input range for x and y is tightly limited between n1 and 100. However, if we use concrete testing, we can discover the error triggering input in just 3 executions. So now let's walk through the process step by step to see how concrete testing efficiently generates such input. First, concrete testing uses the 3 main components, concrete state and symbolic state and past conditions. Concrete state actual values of the program variable, and the symbolic state is the symbolic representations of the variable like alpha and beta. And the past condition is the logical symbolic branch conditions representing the decision made at each branches. So let's take this example input. X is 22 and y is 7. So we initialize the state, concrete state, x is 22 and y is 7, and symbolic state, x is alpha and y is beta. And the past condition is true since there is no branches have been taken yet. So now let's execute the program lines by line with this variable, and we will track the update to all three components as we go. So let's continue that process is the next steps. At the next line, because of these twice functions, the z will be 14 in concrete state and the 2 times alpha in symbolic state since z is 2 times y. Still, the past condition is true as we do not meet any symbolic branch yet. And the next line at these branches, as you can see, z value is not equal to x values. So we go to else branches. And because we encounter a symbolic branches, we will update the past condition by adding this else branch condition, which is z is not equal to x. When we update the past condition, we will use this symbolic variable. So the 2 times beta is not equal to alpha will be updated in the past conditions. Then the first iteration ends because we reach the end of the programs. Then for the next program execution, we won't go into these true branches at the next program executions. To do so, we will negate this past condition, that is 2 times beta is equal to alpha. And we used or employed so-called the SMT solver to find alpha and beta values, which satisfies these negated past conditions. 2 times beta is equal to alpha. First of all, so as you can see, as you can think of this SMT solver as a tool to find a solution in a given equations. Anyway, in this case, the SMT solver can easily find a satisfiable input such as alpha is 2 and beta is 1. As second program execution, we will start with this new input x is 2 and y is 1, where the symbolic state and the past conditions are initialized again. At the next line, z will be 2 in concrete state, and the z will be 2 times beta in symbolic state, and past condition is still true. At the next line, we can get into the true branch conditions because in this case, z and x are equal. And we will update the true branch conditions 2 times alpha is equal to alpha in the past conditions. Next line, at the second branches, x is not bigger than y plus 10. So we go to the else branch conditions. Because we encounter a symbolic branch condition, we add the inner first branches condition, which is alpha is less than or equal to beta plus 10 into these original past conditions. So now the updated condition will be 2 times beta is equal to alpha, and alpha is less than or equal to beta plus 10. Then the second iterations end, and in order to get into these inner true branches, in this time we will negate the second branch conditions, which is highlighted in red. So that is, we call the SMT solver again and find some input which satisfies the formula 2 times beta is equal to alpha, and alpha is bigger than beta plus 10. And we can find that inputs like alpha is 22 and beta is 11. And this test case will be the third test case to be executed. So at the third program executions, we start with this new input x is 22 and y is 11, and this symbolic state and the past conditions are initialized as x is alpha and y is beta, and past condition is true. Then z will be 22, and in symbolic state z will be 2 times beta, and past condition is still true. And next line, we get into true branches. So what we will update the true branch condition in the past condition 2 times beta is equal to alpha. Finally, we reach the inner true branch, the one that triggers the error. So this means we have successfully found the error triggering input. So as you can see, conflict testing is a much more systematic and effective approach compared to the random testings. So it does not rely on chance. Instead, it strategically explores different execution paths. Now let's make the example code as a bit more challenging as shown in highlighted in sections. The twice function has been replaced with a square function that returns the square of its inputs. And let's symbolically execute this modified program again using the initial random input x equals 22 and y is 7. At the next line, z becomes 49 in the concrete state since square root 7 is 49. And in symbolic state, z is updated to beta times beta, representing the square of the symbolic variable beta. And path condition is still true. And at the next line, we encounter a branch comparing z and x. So since z equals 49 and x is 22 in concrete state, they are not equal, so we follow the else branches. In the symbolic state, we will update the path condition by adding the negation of these if conditions. So the updated path condition becomes beta times beta is not equal to alpha. Then the first iteration ends. To explore the true branch in the next execution, we negate the previous path condition, this one. So we now want to find the values of alpha and beta such that beta times equal beta is equal to alpha. So however, here we encounter a common limitation of SMT solvers. So let's suppose that the SMT solver being used does not support the nonlinear constraints, such as squares or multiplication of symbolic variables. Then it cannot solve this constraint beta times beta is equal directly. Although in reality, some advanced SMT solvers do not support nonlinear arithmetic. So let's assume for now that our solver does not. So in such cases, conflict testing tries to simplify the constraint by substituting some symbolic variables with their corresponding concrete values. So this allows the solver continue reasoning about the program even when facing unsolvable equations. For example, we can replace the symbolic value beta with its corresponding concrete value from the previous execution, which is 7. Then the nonlinear constraint beta times beta equals alpha becomes a concrete constraint 49 equals alpha, which now solvable by the SMT solver. So the next input will be x49, x equals 49, and y is 7. So let's now execute the program again with this new input step by step. Okay, so at the first line in concrete state, x equals 49 and y is 7. In symbolic state, x equals alpha and y equals beta. And path condition is true. And at the next line, z equals y times y. So in concrete state, that g will be 49. And in symbolic state, g equals beta times beta. Then at the branch, if x equals g, since x and z all equal to the 49, so we take the true branch and update the path condition to alpha is equal to beta times beta. And next we reach the branch if x is bigger than y plus 10. In concrete state, 49 is bigger than 17 is true. So we again go into inner true branches and update the path condition with alpha is bigger than beta plus 10. So the path condition becomes alpha equals beta times beta, and alpha is bigger than beta plus 10, thereby reaching the error locations. Now the important insight here is that when conflict testing hits on unsolvable or hard constraints like nonlinear ones or external functions, it simplifies the concrete constraint using the concrete value from actual executions. So this allows the conflict engine to continue exploring paths effectively even when symbolic reasoning alone cannot solve the constraint. This is the key benefit of the conflict testing. This time, let's examine the limitations of conflict testing. So in this modified example, the key difference is that the second branch condition has been negated compared to the previous toy code. Now using the same concrete input values, x equals 49 and y equals 7, and we learn the conflict testings. As before, in concrete state, x equals 49, y is 7, and in symbolic state, x equals alpha, y equals beta, and path condition is true. And at the next line, z equals y times y, and concrete z equals 49, and symbolic z equals beta times beta. And then for the condition if x equals z, since 49 equals 49, so we encounter the true branches up, and we will update the path condition as alpha equals beta times beta. And now at the next branch, if x less than y plus 10, so that means the 49 less than 17 is false, so we enter the false inner branches. So, and we will update the path condition as the alpha equals beta times beta, and alpha is bigger than beta plus 10. Now try to the other path into the two inner branches. Concurrent testing tries to negate the last condition, so the updated condition becomes alpha equals beta times beta and alpha less than beta plus 10. Then concrete testing tries to simplify this using the concrete value of y equals 7. So we get the 49 equals alpha and alpha less than the 17. But as you can see, this is clearly unsatisfiable. So that means no alpha can be both 49 and less than 17. So as a result, the assembly solver fails to find a valid input. So in this case, conflict testing fails to generate a new input that leads to the error branches. So this illustrates key limitations. Conflict testing is not a silver bullet. While powerful, it may fail to explore certain paths, especially when simplification results in unsatisfiable conditions. So this is also the well-known limitation of the conflict testing. Now let's finally summarize how concrete testing works at a high level. Concrete testing systematically and automatically generates test case by repeating the following 4 steps. First, it runs the program using an initial random input, for example, x equals 22 and y equals 7. Then during the execution, it records the path condition by tracking the branches taken, say branches B1, B2, B3. These are all symbolic branch conditions. The second step is to generate the path condition. As you know, a path condition is a sequence of branch conditions represented by using the symbolic variable. For example, x and y are symbolically represented as alpha and beta respectively. Then a branch condition like B1 alpha might be expressed as alpha equals 2 times beta. And the third step is to select one branch condition from the path condition and negate it. So we do this in order to explore the opposite side of that branches, just like following the yellow arrow to a new execution path. So in this example, suppose that we choose the B2 to negate among them. Then we take the prefix of the path conditions up to B2 and negate B2, highlighted in red, and feed this modified condition into the SMT solver, and resulting path condition becomes the conjunction of B1 and not B2. So if this condition is satisfiable, the SMT solver generates a new input accordingly. Then returning to the step 1, so after executing the program with this new input, which is x equals 22 and y equals 11, concrete testing records the newly exercised branches, for example, B1, B4, B5. And it also generates new path conditions based on this program execution, which includes the branch condition for B1, B4, and B5 expressed in terms of symbolic variables. Then we choose one of the 3 branches. For example, suppose that we choose the B1 this time. Then we negate the selected branch B1 and feed it the SMT solver and generate a new input and execute the program with this new input. So in this way, by repeating these 4 repetitive steps, concrete testing systematically generates test cases. Lastly, this is a simplified algorithm that summarizes everything we have discussed. So this generic concrete testing algorithm takes as an input a program, a target program P, and an initial input vector V0, and a testing budget N, which specifies how many test cases to generate. And at line 3, the program is executed with the initial input V, and then it generates a path conditions pi, which a conjunction of symbolic branch conditions as shown at line 5. So from the 4 to the 6, the algorithm selects a branch condition, this one, and negate this branch condition and feed the resulting path condition prefix to an SMT solver to find a satisfiable solutions. If this formula is unsatisfiable, select another branch conditions and repeat this process. So this continues until a satisfiable formula is found. And at line 7, a new input generated from the solution returned by the SMT solver. And the algorithm simply repeats this process n time, systematically generating test cases. Okay, so this is all for the symbolic executions. Now let's switch topics and talk about program repair. Just like software testing, I will begin with a question to motivate the topic. Why do we need APR techniques? After that, I will introduce two main categories of program repair, which are general purpose program repair and special purpose program repairs. The key difference is that whether the technique aims to fix all kinds of error or just specific types such as memory or double-free errors. Alright, let's start with the motivations. As you might have already guessed, the debugging takes up about half of the total software development time. The chart on the right shows that, on average, it takes around 200 days to fix a single bug in commercial software. So in this box, the x-axis lists the software like ArgoUML, and PostgreSQL, while the y-axis shows how long it takes to fix bugs. The size of each box represents about 50% of the bugs, and as you can see, the most are fixed within 100 to 300 days. But take a look at the outlier box marked with this cross. In PostgreSQL, for example, some bugs take more than 1,000 days to fix. So this huge debugging cost is the first reason we need automatic program repair. The second reason is also pretty clear. Every year, the number of software vulnerabilities is growing rapidly. As you might know, the CV stands for the Common Vulnerability and Exposures. It is used to identify and catalog publicly known security issues in software. So this graph shows the number of CVs reported in each year. So back in 2010, there were around 4,000. That number jumped to about 6,000 by 2015, and by 2020, it reached roughly 18,000. So the second reason we need APR techniques is that software bugs are increasing significantly. Third, fixing bugs manually like double-free errors or the null point dereference is time-consuming and error-prone, even for experienced developers. So even after the developer believes the issues are fixed, but it's hard to be confident that the fixes are correct. That's because commercial software often spans hundreds of thousands to millions of lines of code. So fixing even one bug in that context is a huge challenge. So to make matters worse, fixing one bug can unintentionally introduce new ones. For example, the code here shows a highly simplified version of a real double-free bug that occurred in the Linux kernel. So to fix this one bug, the developers spent nearly 1 year crafting these 3 different patches, which were reviewed by the 3 other developers. So we will dive into this interesting real-world case later in these lectures. So to summarize, the number of software bugs keeps increasing. Fixing each one takes a long time in practice, and manual fixing is extremely difficult. That's why we need APR techniques. So for these reasons, APR techniques have gained increasing attention from both industry and academia over the past decade. At a high level, we can divide these techniques into two categories: general purpose program repair and special purpose program repairs. General purpose program repair techniques aim to fix all kinds of error, but because of their broad focus, they may struggle to effectively fix certain specific bugs. In contrast, these special purpose techniques are designed to target a specific class of bugs, while not general. They are highly effective for their intended target. First of all, let me give you a high-level explanation of general purpose program repair techniques. These techniques typically rely on a set of test cases to determine whether a generated patch is valid. And a core approach is called generate and validate approaches. So it includes two main components, patch synthesizers and patch validators. The patch synthesizer takes a buggy program and produces candidate patches from a predefined patch space, like inserting or removing a free statement for fixing the memory deallocation errors. Then the patch validator checks whether the candidate patch passes all the given test cases. If any test case fails, the synthesizer creates a new patch and this process repeats. In other words, this approach repeatedly performs patch synthesis and validations, and if a patch passes all test cases, it returns that the patched program as the final output. So now let's consider one downside of these generate and validate approaches. What is the drawback of relying on the test cases to validate candidate patches? The main issue is that it doesn't guarantee the patch actually fixes the root cause of the bug. Even if all test cases pass, the patch might not correctly resolve the underlying problems. So such patches are often called plausible patches in API domains. So these patches appear correct based on test case outcomes, but they don't actually fix the bugs. Now let's say the special purpose program repair techniques. These techniques are designed to handle specific types of errors. Certain classes of errors include memory deallocation errors, null point reference, buffer overflow, integer overflow, and so on. So for instance, leak fix focuses on resolving the memory leaks safely, avoiding introducing the new bugs. The fix another tool aimed at repairing null point reference errors. So in these lectures video, I will concentrate on automatically repairing various memory deallocation errors. So how familiar are you with the memory deallocation errors? Let me explain three common types of the errors: memory, the user after free, and the double free. So these occur when dynamically allocated memory isn't properly deallocated in the language like C and C++. A memory leak happens when the programmer forgets to free a pointer P. And a use after free occurs when the memory is freed before it is used too early. And a double free happens when the same memory is freed more than once. So to fix a memory leak, we can insert a missing free statement for P in this line, free P. And to fix this use after free, we can move this free statement after the last use of the P. And to fix these double free errors, we simply remove one of these duplicated free statement. So the fixes are conceptually simple. So now let's look at why APR techniques focusing on these errors are so important. In this lecture, we focus on fixing memory deallocation errors such as memory leaks, double frees, and the use after free, because they are among the most severe and common bugs in the C programs. This table here shows that these types of bugs are highly prevalent in the major open source software projects. In fact, they occur more frequently than the overflow or integer overflow. For example, this Linux kernel alone has around 6,000 memory deallocation errors, more than the combined number of the buffer and integer overflow. And each of these bugs must be carefully fixed because if left unresolved, they can lead serious security vulnerabilities. And these CB numbers listed here represent only a partial set of real-world vulnerabilities that were caused by the use after free bugs. Okay, now let's look at this toy code, which contains memory deallocation errors. So among the memory leak and double free and the use after free errors, which one is presented in this code? And as you can see, the second question is, can you describe the exact execution path that leads to the error? So I will give you 30 seconds, or feel free to pause this video and to think through it and explain the cause of the memory deallocation errors. Okay, so in this code there is a double free error at line 10. The exact execution path is line 1 and line 6, 7, 8, 9, 10. So specifically at line 1, an object is allocated and stored in pointer P, and at line 7, Q is assigned to point to the same object as P, and this object is then freed twice, once at line 9 and again at line 10, resulting in a double free. Okay, so the next question is, how can we fix these double free errors? I will give about 10 seconds. Okay, so one way to fix this bug is to simply move the free statement from line 9 and to the line 4. Free P. With these changes, this object is freed only once and only when the else branch is executed. So now let's consider an alternative patches. What if we instead move the free statement from, okay, let me erase this one. So the alternative patch is, what if we instead move this free statement from the 10 to line 4, free Q, and left line 9 unchanged. That would actually introduce a user actor free error occurring along the path line 1 and line 3 and then line 8. So even with this small code snippet, you can see that the fixing the bug is not trivial. Okay, so now let's look at a more complicated error based on a real bug in the Linux kernels. So we will walk through how Linux developer manually fixed this bug and then how an API technique can automatically do the same. So in this simplified version, line 1 and line 1 to 5 allocate and use and deallocate two buffers in and out. And line 7 and 13 attempt to reallocate in and out to a little bit larger size. And as you might know, when these buffers in and out fail to get reallocated at line 7 and 13, and in this case, this buffer will return the null respectively. So in this case, go to the error handling code at line 20, which deallocates the buffers in and out. So in this code snippet, there exist two double-free errors. So I will give you the 20 seconds. So look for the bug trace yourself. Okay, so the first trace goes like this. When the memory allocation fails and the malloc function returns null, as I mentioned before. So if execution reaches at line 9 or line 16, it means the memory allocation fails because we enter the true branch of the if statement. So if the reallocation in at line 7 fails, the program jumps to the error handling block at line 20. So there it calls free on out, which already freed at line 4. So this results in the first double free errors, free and go error and free again. Similarly, when malloc at 13 fails, the buffer is freed twice, once at line 15 and again at line 21. So now that we have identified both double free errors, so the next question is how can we fix them? So please pause the video here and try to fix the two double free errors on your own. This modified code shows the initial patch made by Linux developers. So to prevent the double free errors, the developers set the buffers to null at line 9 and line 16, as highlighted in yellow. As you might know, once a pointer is set to null, it cannot be freed again. So therefore, a common memory handling practice is immediately set a pointer to null right after freeing it. So for example, brief P and free equals null and the brief P, executing this sequence does not trigger a double free error because the pointer is properly nullified. So now let's examine the two double free error traces to see whether they are properly fixed. The first error trace was along lines 4 and 10 and 22, highlighted in green. The buffer out was freed at line 4, then nullified at line 9, and later freed again at line 22. So thanks to this nullification at line 9, so this trace is now safe. And the second error trace follows the line 15, line 17, and the 21, highlighted in pink. So due to the correct nullification of the buffer in at line 16, this trace is also now safe. In other words, when in or out buffers fail to be reallocated, they are assigned null, making the subsequent free calls safe. So although this fix is not minimal or ideal, but it's still correct. Here's where the first challenge of the manual debugging arises. It's hard for developer to ascertain that the original double-free errors have been fully or correctly resolved. Right now, we are looking at a simplified 22-line version, but the original code spans several thousand lines. So in such large code bases, it is easy for developers to get confused while trying to understand and fix the errors. Unfortunately, the Linux developer mistakenly believed that a double-free error still remained in this code. To address these perceived issues, the developer created a second patch moving the free statement from the line 4 to the line 20. So the likely intention was to follow a common memory handling practice, inserting a free statement just before allocating new memory to pointers. However, this change introduced a new memory leak that did not exist in the original code. So here's what happens after the buffer out is allocated at line 1, and if the allocation for buffer in fails at line 7 and out is nullified at line 9. As a result, the object originally pointed to by out becomes unreachable, which risks memory leaks. So this highlights the second major problem of manual debugging. While developers try to fix one bug, they can unintentionally introduce new unexpected errors that were not even present in the original source code. So this memory was later reported by another developer, prompting the original developer to create a third patch. To fix this leak, the developer moved this free out statement from the line 20 back to its original positions at line 4. In addition, they nullified the buffer out at line 6 to prevent the imaginary double free. The result code was error-free, but it ended up being even more redundant than the first patch. In total, it took about 1 year to resolve these double-free errors. 3 patches were written, and the 3 other developers reviewed this code. For your interest, the developer involved was Linus Torvalds, the creator of the Linux kernels. By looking at this real-world fixing process, I hope you can see just how difficult it is to fix these kinds of errors manually. Okay, so from now on, I will introduce a state-of-the-art APR technique called memfix. designed to automatically repair memory deallocation errors. The key feature of this technique is that it guarantees the correctness of the generated patch. In other words, it does not produce plausible patches that merely pass all test cases without truly fixing the bugs. And Mapmix also ensures that no new errors are introduced during the repair process. So to accomplish this, it relies on two core ideas: static analysis and solving the exact cover problem. So let's now explore how this technique automatically generates correct patches for the memory deallocation errors. First, let's start by looking at the output produced by Mapix. As you can see, Mapix fixes the double-free errors with just two simple changes compared to the original buggy code. As you can see, it removes the free in call at line 15 and moves this free out statement from line 4 to line 12. So the core idea behind this patch is to deallocate buffers right before they are reallocated. A simple and minimal solution for the original problems. So the intuition behind the Mapix strategy is to place the free statement immediately before this object is reallocated. For instance, the free for in inserted just before a realloc at line 7. Similarly, the free for out is inserted at line 12 just before the realloc at line 13. So this allows us to fix code without introducing extra nullification statement, unlike the patch written manually by Linux developers. As I mentioned earlier before, the Mapix provided formal guarantees that the generated patch is correct. So as a result, it frees developers from the tedious and error-prone task of manually verifying the patch's correctness. To achieve this, Mapix reduces the problem of finding a correct patch, more specifically identifying the correct set of the free statement into solving exact cover problems. For those of you who may not be familiar with the exact cover problem, I will give a brief introduction first, and then I will explain how Mapix uses this idea to automatically fix the memory deallocation bugs. The exact cover problem is a well-known NP-complete problem. So using this example below, solving it means selecting a subset from the set labeled A, B, C, D, E, such that the selected sets together cover the numbers 1, 2, 3, 4, 5 exactly once without no overlaps. So in other words, you need to choose a combination of subsets where each number appears only once across the selections. So since there are 5 sets, the total number of possible combination is 2 to the 5, which is 32. So can you find the correct subset that satisfies this exact cover? So I will give you 10 seconds. All right, suppose that we select a subset containing A, B, C, but however, this is not an exact cover because the number 2 appears in both A and B, B and C, meaning that it is included twice. So for a valid exact cover, each number from 1 to 5 must appear once and only once across the selected subset. Now suppose that we select another subset A, B, D. This does form a valid solution to exact cover problem because the numbers 1, 2, 3, 4, and 5 are each included exactly once with no overlaps. Interestingly, Memfix takes a similar approach. It transforms the task of fixing memory deallocation errors into an instance of the exact cover problems. Now, let me explain how Memfix works using this small code example I showed earlier. So let's revisit this code. So it contains a double free error along with the execution path line 1, lines 1, 7, and 9 and 10. At line 7, both Q and P refer to the same object, and that object is then deallocated twice, once at line 9, again at line 10, which results in a double free error. To fix this double free error, Memfix first uses the static analysis to enumerate all possible object traces. So in this work, each object trace represents how a particular object behaves along a single execution path. So let's assume that the object allocated at line 1 is called O1 and the one at line 3 is O2. So for example, the first object trace corresponds to O1 along the true branches highlighted in yellow. So in this execution path, both O1 and O2 are allocated and both are eventually accessed via the pointer Q at line 8. And the second trace shows the behavior of the object O1 along with these first branches. In this path, at line 1, O1 is allocated and assigned to the pointer P, and at line 7, the Q is assigned the value of P, so both Q and P now refer to the same object O1, and at line 8, the object is used through the point Q. And the last trace corresponds to the object 2, which appear only in the true branch. In this trace at line 3, O2 is allocated and assigned to pointer Q, and at line 8, the object is used through the pointer Q. So since the O2 is only allocated in the two branches, it has a single execution path. So in summary, the first step of the Memfix is to enumerate all object traces, each representing how an allocated object such as O1, O2 is used and deallocated across the different execution paths. So in this toy example, there are 3 object traces. Okay, so after enumerating all the object traces, Memfix proceeds to define safe patches for each trace. So let's go through these step by step. So for the first trace, object O1 in the true branches, the object O1 is allocated at line 1. So we can safely insert brief P after line 1 and line 3 or line 8. So these become the candidate patches to deallocate object O1 for this trace. And the second trace, object O1 in the first branch, the object is again allocated at line 1, and the candidate patch include free P after line 1, and free P or free Q after line 7, free P or free Q after line 8. And lastly, the third trace, object O2, allocated in the true branches. It is allocated at line 3, and we can insert free Q at line 3 or line 8 to safely deallocate it. So in this way, MemFix first enumerates all valid patch candidates per trace, and each representing a location where this corresponding object can be deallocated. Next, we eliminate the unsafe patches, those highlighted in red, so from the set of the candidate patches. So these are considered unsafe because they deallocate the object P or Q to OLE, specifically before the object is used at line 8. So this could result in a use after free, which we want to avoid. So by filtering out these OLE deallocations, we retain only the safe patches that preserve the program correctness. We also remove the free P statement at line 1 from the first object trace. The intuition here is if a free statement is unsafe in one trace, we treat it as unsafe in all traces. So previously, we identified inserting free P at line 1 in the second trace could read use after free error. So therefore, we remove the same patch free P at line 1 from the first trace as well. So this ensures consistency and avoids the introducing errors across the overlapping execution passes. Now, after removing all the unsafe patches, so we finally solve the exact cover problem using this table on the lower left. So let's define each object trace as T1, T2, T3. In these tables, each column corresponds to an object trace, and each row represents a candidate patch and which traces it safely cover. So what is the solution to the simple exact cover problem? I will give about 5 seconds. As for the exact cover problem, if we choose both free P at line 3 and free Q at line 8, and we get a valid solution to the exact cover problems. And surprisingly, this solution also corresponds to the correct patch that fixes the double free error. With these patches, each object is deallocated exactly once across all traces without causing any double free or use after free errors. Okay, so for another example, if we choose both free P at line 8 and free Q at line 8, this is not a valid solution to the exact cover problems. And moreover, this choice would introduce a double free error since both P and Q may refer to the same object at runtime and deallocated at the same point. So this is double free errors. So by applying the solution to the exact cover problem, MemFix generate a correct patch that removes the double free error without introducing any new bugs. So that is to fix various memory deallocation errors, MemFix first performs static analysis to collect patch candidates for each allocated object. Then it reduces the task of selecting a correct patch to solving an exact cover problem over those allocated objects. So in this case, MemFix automatically inserts free P at line 4 and it removes the free P at line 9. And this is, as you know, this is the correct patches. Now let's briefly look at the MemFix performance in practice. So the evaluation was conducted using the 24 programs for core utilities, and specifically they tested whether MemFix could generate safe, and correct patches for version of these programs where all free statements had been removed deliberately. And Mempic's performance was then compared to the LeakFix, another state-of-the-art APR technique focused on fixing the memory risks. As you can see, this result, Mempix successfully repaired 15% of the programs, while the LeakFix managed to repair only about 13%. So this means Mempix significantly improved repairability compared to the existing technique LeakFix. However, when we examine the size of the evaluated program, as you can see, we can see the limitation of scalability. So, because Mempix was applied to the code bases ranging from roughly 500 to about the 3,000 lines of code. So this is key limitation when applying the Mempix to the more complex code bases. Okay, so to summarize this gentle introduction to software engineering, this course offers an engaging journey through the full life cycle of software development, from writing documentation to implementing software, identifying bugs, and applying various techniques to fix them. So we have touched on key concepts in this course such as software testing, especially symbolic executions, a representative white box testing method for uncovering bugs. And we also explored some automatic program repair techniques for safely fixing errors like memory deallocation bugs such as memory double free and user free. So I think this course will be both important and enjoyable. So I look forward to seeing you in this class. Okay, this is all for today. Goodbye, everyone.